Yes, thank you for the introduction. And hello, everyone. My name is Haiyang Yu. I currently work at Uppsala University in Sweden as assistant professor. And before that, I did my PhD in NTNU with Professor Zhiliang Zhang and Professor Jianying He. And then I did my postdoc in Oxford with Alan Cox and Ed Houghton. And they are my collaborators. Thank you.
Yes.
And today, I would like to introduce to you a potential approach which could be helpful for visualizing the interplay between hydrogen and dislocations or localized plasticity. Since this session is dedicated to hydrogen embarrassment, I believe there's no need to reiterate the basics. But I think what we need to keep in mind is hydrogen embrittlement is featured by a global reduction in ductility as well as a local transition from ductile to brittle fracture. And there has been sufficient experimental evidence showing the existence of plasticity under the seemingly brittle fracture introduced by hydrogen. And this highlights the important role of dislocations or localized plasticity in hydrogen embarrassment. In the literature, there have been several theories about the interaction between hydrogen and dislocation. There are opinions that hydrogen would promote dislocation emission, multiplication, and mobility. But there are also sufficient evidence, mainly on the optimistic side, claiming the opposite. But anyway, I think a general consensus in the community is hydrogen embarrassment is really complex, and we may need a more than one theory to explain the phenomena, and this is dependent on material and loading conditions. So in order to really dig into the interactions between hydrogen and dislocations and visualize the interaction, here I would like to try to sell to you an approach which is called discrete dislocation dynamics. In this approach, we discretize dislocation lines into straight segments so that we get a bunch of nodes. And in each time increment, we can evaluate the nodal velocity of each node so that we can capture the entire evolution of the dislocation structure. And with this approach, it is possible to simulate some elementary processes of dislocations, such as the operation of a Frank-Ridge source, formation of dislocation junctions. If we put these elementary processes into a finite volume, and let me see, there's an issue with the, yeah, so if we put the, if we put the elementary processes into the volume, well, now what you see is just the elementary processes, but there should be a box surrounding it. So that is the finite volume, okay? So if we consider a finite volume and couple the dislocation dynamic simulation to finite elements approach, we will be able to simulate the operation of the dislocations in the volume so that we can capture the microscale plasticity in a real microscale experiment. And further, we can introduce hydrogen into the dislocation dynamics framework. And we do this by considering the hydrogen modified velocity of dislocations as well as the hydrogen lowered dislocation energy profile. If the energy is reduced, the line tension of the dislocation will be reduced, and dislocations will be more easy to be generated. So this is the general idea. And with this framework, incorporating hydrogen, we can simulate a very clean material system. This is a single crystal, and we look at a single slip system so that we can accumulate a dislocation pileup after applying load. And if we simulate the dislocation pileup with and without hydrogen and overlap these two figures together, so The black solid lines represent the dislocation lines when simulated without any hydrogen. And after hydrogen is added, we get the blue dashed lines. All the other conditions are the same. And what we can see is hydrogen can reduce the spacing in the dislocation polyp and indicating that hydrogen will increase the local dislocation density. And this is also in accordance with the famous experimental evidence reported in the 1990s. And also, knowing that in the engineering practice, the materials are mainly alloys. So we tried to add a inclusion or precipitate into the pure metal, and we were able to simulate the dislocation entanglement with the approach around the precipitate, like this. And again, we simulated the scenario without and with hydrogen, and we get these two entanglements. What you can tell is with hydrogen, the entanglement density and also the complexity are increased a bit. And further, if we analyze the dislocation, if we analyze the total stress field exerted by these two dislocation aggregates, we can see that for both cases, the stress field looks different. In the case with hydrogen, we are seeing a lot more high spot regions, meaning that hydrogen could promote the possibility of stress concentration, and it could increase the propensity of crack initiation. So this could be qualitatively related to hydrogen-promoted fracture. So all the results presented earlier are about the influence of hydrogen on dislocations. But in my title of the talk, I mentioned we have interaction, meaning that the influence should be in two directions. So how do the dislocations influence hydrogen distribution and diffusion? Well, we recently used the dislocation dynamics as the basis to simulate hydrogen diffusion. So in this figure, I show the results obtained by the conventional approach, where we just use a classical Fickian diffusion. So hydrogen diffuses from the bottom upwards, and we consider the Orion-Ennis trap. Basically, we have a trap binding energy and density, and then we consider the trapping effect. In that model, all the traps are assumed to be homogeneously distributed across the volume. So it's smeared across the volume. And because of that, if we do not have external loading, if we do not have externally applied stress concentration, all the simulated hydrogen profiles will be uniform. So if you look at the same height, we have the same concentration. That is because the trap is smeared in the volume. But we know that in reality, we have dislocations, and dislocations are trapping size. So could hydrogen actually distribute in a non-uniform way? Well, we can use this approach to check it. We simulated first dislocation dynamics and get this kind of a dislocation structure. And then, as mentioned, we can evaluate the dislocation stress field, and from the stress field, we can extract the hydrostatic stress field, as well as the gradient of the stress field. And then we apply this classical modified Fickian diffusion to simulate hydrogen redistribution. What is important is, in this process, we do not explicitly consider any trapping parameters like trap density, trap binding energy. We don't consider them. And this is our simulated diffusion profile. And apparently the diffusion is non-uniform. And this is in contrast to the uniform profile I presented earlier. And the reason is exactly that we considered the discrete dislocations, and their stress field directly governs the hydrogen distribution without explicitly considering any trapping effector. And this is done in Abacus with a user-defined subroutine. And we also compared our results to the Abacus embedded diffusion, which the previous presenter, I think he used this platform. And we can see good agreement, which adds to our confidence level. And further, if you compare the non-uniform distribution profile with the discrete dislocation structure I showed earlier, and this is a 2D view, you can see that really it corresponds to the locally accumulated dislocation polyps. So with this approach, we show the possibility of using DDD to directly simulate hydrogen diffusion and redistribution. And in the future, we could use this approach to calibrate the dislocation density and dislocation binding energy, and we can compare it to the experimental values. And further, this provides a way to really link hydrogen redistribution to the microstructure. So this could be a potentially promising approach, I believe. But the key drawback of the approach is it can only simulate single crystal for now. So I have to warn you about this. Yeah. This is a brief summary, but to save time for questions, I would skip this one. And thank you for your attention.